Good afternoon. So in this session, I will talk about something interesting in Android security, especially the security of ASoC drivers in Android kernel. Before this talk, let me introduce myself at first. My name is Shen. I'm currently working as a security researcher and solution developer at Shen Micro. My focus is on advanced mobile server research and exploit detection. I have over 7 years in security industry. Since 2015, I began to disclose Android bugs. And personally, I'm hunting bugs not for exploitation, but for deploying protected solutions. You may reach the following 2 blogs to get some typical articles from me. So for your information, what will be covered in this talk? I will go through some bug hunting experiences in Android Media framework. This include both the user space and the kernel space bug hunting. And there will be some typical kernel bug review. I will introduce why and how this bug happens. And there will be also a potential exploitation chain targets these bugs. By introducing this, we will know how to reach these bugs. And there will be still some tips to kernel developers, especially ASoC driver developers for their secure coding. And what will not be covered in this talk, don't expect a detailed exploit introduction or a demo, because that is currently not my focus. And this research discloses the following kernel bugs. All of them are kernel bugs and media related in less than 1 month of a dedicated bug hunting. I should say that before this talk, all of the bugs have been already responsibly disclosed to vendors and now be fixed. Okay, so the agenda. First, I will give a background and introduction of why I did this research. And then I will give you an example of how to fuzzing a user space media model in Android. And there will be also some introduction of the ASoC and ASoC in kernel, the advanced Linux sound framework, which was inherited by Android. And I will also give analysis about the attack surface and what is the issue. And there will be also some typical kernel bugs go through, and some thinking in exploitation, and finally a conclusion. So the background, why did I do this research? Since 2015, the Android media server bugs, there is a burst of bug disclosure since August of 2015. This is because during that time, the Google launches the Android bug bounty project, the Android VIP. And the first media server bug about the lib stage fright was disclosed in 2015, in 2016 Black Hat. So in 2016, this media server bug spread from the lib stage fright module to OpenMax, and finally to software and hardware codecs from the upper level to the low level. And most of the user space media modules are affected. So it quickly becomes a Red Sea. But however, few bugs in kernel of that part were disclosed before my research, before the second half of 2016. So that's why I decided to do this research. So let's quickly have a general review that why and how media bugs become so hot in Android. If you look at the history of the Android security bulletin, you will find that since 2015, Android media server bugs, there are about half of bugs are media server bugs. This is ridiculous. And even in 2016 and 2017, there are also about 20%. All of these bugs are media server bugs in user space. And besides that, most of these media bugs are assessed as critical or high severity by Google. So The reason could be possibly because there could be 4 reasons. The first reason may be that media bags are born with the remote gene because based on the Google VIP policy, a remote bag maybe get a higher bug bounty and a higher severity assessment. So basically this means higher bug bounty, and even it is only a DOS. And still the real life exploitability has been proved. In 2016, the Northbit has open sourced a working exploit, which named as the Metaphor, targeted at lib stage fried vulnerability. And the last reason may be that these meter server bugs are easy to fuzz. But is that true? I will give you an example. So how is it easy to get a meter bug? Let's do it. So before to hunt meter server bugs, we should know that which media module should I get to hunt bugs. So in order to practice an effective fuzz experience, I choose the AFL, American Fuzzy Loop, because it is a coverage-based fuzzing tool, very effective. And for the target, because I only want to fuzz a single module with less dependency, because in general, if the module is more dedicated, it possibly means that your fuzzing will be more effective. So based on this, the third-party modules in the external directory, which is located in the ASoC Android open source project, are in scope. So I go through all those modules in the external directory. I find that there are some modules are specifically media related. Most of them are software codecs, such as libavc, libhuvc, and libmpeg2, libvpx. All of them are working as a software codec. So before finding, there are some tips. You would better not fuzz with the test codes in those libraries because the Android OS invokes them differently. And second, you need to understand how Android invokes them, because only based on this that you can write a POC quickly when you find a crash. So let's see how software codec API are invoked in Android. So basically, there is a function in Android OS framework named onQueue field. This is a function that serves as invoking the codec API to decode the buffers or encode the buffers from the media file. So basically, the loop will loop to get the buffer from the media file and to set some decoder arguments, and then invokes the API function. So there is a parameter in this IVDEC API function. This parameter reference to our user space buffer. This is the codec buffer. So this is a typical scenario that Android invokes those software APIs. So what is the codec data? Let's open up a media file. You will find that it's not far away behind the first beginning of the media file. There was a buffer. In this example, it's FF. All of them are FF because I crafted. So this are typically the codec buffer that encapsulated in the media file. So we can emulate this codec data and pass it in the media file, and let Android OS framework to parse this and decode this. That will be a typical fuzz scenario. So how to fuzz? I know how Android invokes these codec APIs, and I get an arbitrary buffer data, which can be passed to the codec libraries to invoke them to do some encoding or decoding logics. And the buffer can be easily built into media file. I just need to replace that part in the media files. So, and also the codec modules are less dependency. This means that it can be easily to be built with AFL. So this is a typical scenario that AFL perfectly fits. So what should I wait? Just write the code and test it. So this is after run about 1 day, several hours, I got this result from the failed. I got hundreds of unique crashes and hangs. After confirmation that all of these bugs are valid bugs and all of them are removable bugs. So this is my codec file that it always covers most of software codecs, decoders, and part of software codec encoders. It has been proved to be extremely effective, and I have already open sourced to Google, to Android security team. So this is just the beginning of this talk. This is not the real focus. So the next I will, let's move to the kernel part. I could imagine that there should be two parts in kernel part that handle major things. One is for Android audio. The other is for audio, video. That could be audio driver and a video driver. So this time I decided to look at the audio part. So let's look at the Android audio architecture. So you can, from the picture that you can find that the upper level, the media player applications will invoke the media server through the binder IPC, inter-process calling. And the media server processes will finally call the underlying Linux kernel drivers through the HAL. So based on the Android security bulletin, there are a lot of CVEs disclosed to the both the media server part, the audio server part, and also the HAL part. So, but it's quite strange that before the June of 2016, there are only 4 CVEs disclosed in the Linux kernel part. So I can't believe that. So this is why I decided to look at this. So there could be comes a question that how many bugs for a module should be acceptable? So based on the code complete, so in 1992, Microsoft has reached a half detect per KROC. This means that every 1,000 lines of code, there could be only a half defect. So this is the standard of the Microsoft in 1992. So if we follow the Microsoft standards, I have calculated all the sound driver related coding in the kernel. This is a Qualcomm device, so most of the code are from Qualcomm. So there could be more than 250,000 lines of C code. So if we follow the Microsoft standard, there could be more than 100 bugs, but we currently have 4. This is a very strange scenario. So I suppose that there will be a lot of things that we still have a long way to go. So what is the ASoC? ASoC is Advanced Linux Sound Architecture. That is a software framework and a part of Linux kernel that provides application programming interfaces for sound card device drivers. It's basically the sound card, sound management of the Linux kernel. So it is started in 1998. Very old, had a very old history. And they replaced the previous open sound system since kernel 2.6, and it is inherited by Android. And the ASoC specifically means that the ASoC system on chip. It's basically a sub-project of ASoC. It was designed to especially for mobile devices. For example, the mobile device has some different functionalities with the traditional desktop Linux platforms, because, for example, the sound control, the power management is different. So that's why this ASoC project is developed. So this is the whole architecture of the ASoC. You may find that there is a machine, 3-module machine, platform, codec. The machine could be like some motherboard or our mobile devices. And the platform, like the processor for the ARM processor. And the codec is the sound driver. So from this architecture, we can see that the codec, the main functionality of the codec driver is to transform the digital audio to analog audio. So it has also a direct interface to co-work, to communicate with the processor. So what is attack surface? Taking this Nexus 6P, for example, you may find that there are so many character devices under the device sound this pass. Basically, there are 5, the control device, and the compressed device, and HWDP, and the PCM playback and capture. Each device has different functionalities. But for one sound card, there could be only one card number. So you may find that the control device only has one character device, that's control C0. But for HWDP and playback and capture, there are a lot of other devices because they have different functionalities. And there are second attack surface that under the device, there could be some vendor-specific character drivers. For example, in Qualcomm device, there are some AAC driver or AMR MB driver. So this is specifically designed for hardware decoding or encoding. So let's first take a look at the control device. So this is the struct that serves the control device. You may find that there are 3 function pointers: the info, the get, put. These 3 function pointers are user-accessible interfaces, which means that the user space code could invoke the kernel space code through these 3 different function pointers. So there is the assumption that if we know that how user space code invokes these 3 function pointers, then we can know how to fuzz the kernel. So let's see. From the kernel code IO control that responds to this user space command, you may find that there are info, sound IO control, card info, and read, write. So let's first check the read. The read is corresponding to the put. So if user's space code call this write command to the kernel, it will firstly pass the buffer user buffer control. The structure is a sound control element value. This buffer is from user space, and finally call the sound control element write with the same buffer. The buffer then in this function, it will firstly find the ID, get the control object, and use this control object to finally call the function pointers. So if we want to invoke this put interface, we should firstly find the control object. The control object is found based on the control ID. So we need to know what is the control ID. So this is basically the user space buffer. You can find that the first element is the sound control element ID. And the third, the union buffer, which these buffers are typically from a user space, but have different type. So what is the element ID? Let's check the function that uses this ID to find the object of control. You will find that finally it will compare this ID, num ID under this ID structure to check if the ID matches the current control object. If it matches, it will return the control directly. So I could guess that maybe this num ID is incremental from 0. So is that true? I write some code to dump the ID in my Nexus devices. From this dump, you may find that this num ID is indeed incremental from 1 to more than 1,000. So there could be so many control objects. So that could be potentially a big attack surface. So the next is that we need to know how this input is used. Because we know how to get the control, then we should know how this put or read is used. So from the take a piece of some code, we can find that, for example, this control is firstly passed to the global variable MSM slam file XCH, And then this global variable is again passed to a local variable. This local variable IXH count, and finally passing as an argument in this function, sound ASoC set channel map function. So it seems that this user space value is used so complicated. So the logic seems very complicated. So how many puts in the kernel? Let's search it. After grab this structure, I find that there are more than 2,000. It means that possibly there are more than 2,000 code snips that will invoke this put from the based on the user space buffer. So this could be a very big attack surface. So the next step is just to fuzz it. So it's very simple to write the following less than 10 lines of code to fuzz this kind of logic. The first, I open this control device, and I craft a very big value to this user space buffer, and I keep the num ID incremental from 1 to more than 1,000 or 2,000, and use this element IO control element write command to invoke the IO control to pass it to the kernel directly. So what is the result? The result is surprising. So I got a dozen of kernel crash happened continuously. Even I fix one of those bugs, there could be continued dozen kernel crash happened. After checking these bugs, I find that these bug types almost cover all the common bug types that we are facing. For example, stack overflow, heap overflow, and use-out-free REST conditions. It seems almost the common bug types are covered. And this is a buggy ecosystem. It should be said that this defect code is not only in one vendor or two vendors. The whole ecosystem is affected. So for example, the ASoC project, the Qualcomm, NXP, NVIDIA, DTS, even the device manufacturer, for example, OnePlus. So let's go review some of the typical bugs. For example, for Qualcomm device codec driver, there is the case 1, out-of-bounds access. Because this the code takes the buffer, the control buffer from the user space directly, and there is no sanity checking. And they use this value to do as an index of the array. So that will directly cause out-of-bound access. Non-pointer dereference, because there is no checking. Some before the pointer used, it doesn't checking if it's null. So it will directly lead to a null-pointer MPD. The heap overflow, because this value also, it has not checked the validity. So it used to as in a loop, as an index in a loop. So this will definitely cause a heap overflow. And also there are type confusion bugs. Because Qualcomm incorrectly uses this structure, so this will cause the type confusion and lead to kernel crash. So this is a typical four bugs that I share with you. A lot of bugs are skipped here. I will not go through one by one. And so we just talk about the put, which is that user space code writes something to kernel. But what about the get? Possibly that it means that the user space code will read something from the kernel driver. So, but basically the get is difficult to be fast to lead to kernel crash because it only will leak some sensitive data. So I decided to audit the code. This is a typical example that there is an uninitialized stack variable leakage. This is Qualcomm code. that this group, this array, local array, has not been initialized, and that there is no return value check after the calling, check after the passing value, and finally, it will be passed the value to the user space control buffer. So it will be lead to a kernel stack leakage. Also, information disclosure. There is also the user space buffer is used as an index in a loop, and there is no any sanity checking. Integer overflow and heap overflow. Also, because of the lack of sanity checking of the user space value. So this is all about the Qualcomm code. So I could guess because this is also a framework, is a common framework, that many different devices with different hardwares maybe have the same logic. So what about if other vendors have also this kind of problem? So this is a crash that happened during my fast. I find that in our ASoC project, there is also a stack overflow problem that there is an index used in the loop as an index of the array, but it didn't check if it had reached the max value. So it will definitely cause the stack overflow and the kernel crash. And also, I looked inside some NVIDIA devices. The NVIDIA Tegra 210, there are also sometimes a lot of code have the same logic. They will also get the value from the user space, and there's no sanity checking, just use it directly. This is the buffer overflow case. This is also a buffer overflow case. Outbound access. So this is NXP. So after reviewing so many bugs, that I find that it may be a common problem that kernel developers, misunderstand of this logic. There may be some common issues happened. The device which I tested, I only tested 3 devices: Nexus 6P, OnePlus 3, and Pixel C, because I only have these 3 devices. I have not tried the other yet, but I basically could imagine that there could be more than other vendors affected by this kind of problem. If you are interested, you may test it yourself. So what is the problem? Let's review it. So this struct user space struct that passed in a get port is originally designed to get and write values from or to the codec hardware register only. Basically, it is only used to read and write values to the codec hardware register. It shouldn't be used so complicated to some logic that is very complicated. So it is a kernel buffer, but its data is coming from user space. It's often misused by kernel developers to do some complicated things, but without sanity checking. So this exposes a wide range of kernel code to user space. And possibly because the ASoC project made it for design, but actually the vendor, the codec developers made the implementation. There could be some gaps. So we have just talked about the control, but what about the others? Because there are a lot of attack surfaces of the sound driver. This is hardware DEP. This is DTS, the code, the defect code from DTS. The rest condition will definitely cause UAF or double free. There is no some lock for this global variable. Sec blob is a global variable, but there is no. It doesn't keep it as there is no lock to control this. So if two rest condition to call this, there will be definitely a rest condition. Will definitely lead to UAF. Also, the playback and the capture, they're also used after free. Some pointers is freed, but not set to null. This will lead to a dialing pointer, and when I call it from the port interface, this pointer will be reused, and this will finally cause the use of the free. Also, in hardware effects, there are a lot of out-of-bounds access. So we have just reviewed some typical that bugs. What about exploitation? So in this talk, I will not go through the detail how to exploit these bugs because that kind of not my focus. But I will introduce some thinking in how to exploit these bugs, especially how to reach these bugs from a third-party application or unprivileged application. Look at this sound driver. It can be only accessed from the processors that within the AID audio group. So I checked all the process that in this AID audio group. I find that most of the system applications and the system media related server processes are in this group. For example, the audio server, the camera server, media server, and the system server, and also some Google GMS or some other system applications from Google. So basically, if we want to exploit these kernel bugs, we should firstly compromise these system applications or system servers. So is that possible? Let's look at the Android security bulletin in this year or last year. We find that there are a lot of media server bugs or system server bugs, audio server bugs are disclosed continuously. A lot of. Most of them are privilege escalation bugs, which means that a third-party application can exploit these bugs to get the code execution in media server, these privilege processes. And so there could be two proposals that reach these kernel driver bugs. The first one is the chaining from the system server. Google Project Zero has proved this, that with a single bug that gain the system server code execution. So we could leverage this bug from a local application to compromise the system server. We get the code execution in the system server, then we get the access privilege to the sound driver, kernel sound driver, then we can do code execution in sound driver and finally get the root privilege. This is a local root case. And the second proposal is that we can chain in from some audio media server bugs because even in July in this month, there are still a lot of remotable media server bugs reported based on the Google Android security bulletin. So we can exploit these media server bugs to get the code execution in audio or media server processes. And finally, based on from the media server process, we can get code can reach these bugs. So by exploiting these sound driver bugs in kernel, we can finally, at most, get a remote root exploit. So Northbit has proved this in their metaphor, real-life working state for the exploit, that from a remote media file to get the code execution in media server. This has been proved and open sourced in GitHub. So, but there could be some challenges because Google might get the media server bug since Android mesh model. So, if you want to explore through this way, for example, explore through the media server or the audio server, that will be definitely difficult because those privileges are separated and restricted with limited access privilege. And you may need to handle additional bugs to break this limitation or restriction. So the conclusions, The first, kernel developers use this get put interface to configure the ASoC SoC codecs, but often miss sanity checking. And this opens up attack surface in kernel, but this attack surface will usually be overlooked. So local or remote route is theoretically possible by chaining these bugs from system media or audio camera servers. And the ASoC drivers should be careful when handling these get or put interfaces and keeping user space values as simply used to write or read codec register only. So the main problem is still that the author project designs the logic and how to use this code to communication from the user space code to kernel code. But unfortunately, the kernel developers, most the codec driver developers misunderstood this. So they think that the control buffer is really a kernel buffer or something else without do any sanity checking before you use it. And also they use this kernel buffer, user space buffer to a lot of complicated things, a lot of different complicated logic. So this leads to this issue. Okay, so this is my sharing. So any questions? Okay. OS. Definitely, I didn't try the OS, right? But I think I'm not sure the OS kernel use the same driver or different, but maybe different. So if it uses a totally different framework to control this codec driver, so that will be not affected. But I'm not sure of this. Additionally, because these bugs need to be accessed from the privileged process, which means that a third-party application or an unprivileged application cannot to call these bugs reach this bug directly. You should first chain additional bugs to get the system server privilege, and then to finally to compromise the kernel. So that may be also different in iOS. Almost same. Yeah, that may be a big opportunity. So any other questions? Okay, so if you have any questions, you can ping me from the Twitter or my email after this talk. Thank you.